Welcome, everybody. I want to give an introduction to the duality of linear programming. So let's just start with a linear programming problem and follow our noses. We're trying to maximize 2x1 plus 3x2 subject to these various constraints. And we have our non-negativity constraints on our two variables, x1 and x2. Two variables, three constraints. So even before I solve this problem exactly, by eye, we can sort of find some bounds on how good we think the optimum could conceivably be. So one thing that, just looking at this, I'm noticing that 2x1 plus 3x2 is bounded from above by one of my constraints. So that's bounded from above by 4x1 plus 8x2. And that's by the non-negativity of x1 and x2, right? x1 and x2 are non-negative. So certainly 2x1 is at most 4x1 and 3x2 is at most 8x2. Okay, and then I know that 4x1 plus 8x2 is at most 12. So boom, I already know that, you can't do any better than 12. And let's keep playing this game for a bit. So instead of taking this first equation and using that as my bound, I really could have divided it by 2. Because if I divide it by 2, this is 2x1 plus 4x2. And 2x1 is still at most 2x1, and 3x2 is still at most 4x2. Right? So this is at most 1/2 times 12, which is 6. So I've done even better, okay? I can see that, yeah, the best you can do is at most 6. Let's keep searching. So I won't really tell you how I or the book found this next one, but it turns out that if I take 1/3 of this equation plus 1/3 of this equation, I can get an even better bound. So 2x1 plus 3x2, what we're trying to optimize, is at most 1/3 times my first equation plus my second equation. Okay, just because I have 1/3 of 6x1, which is equal to 2x1, and I have 1/3 of 9x2, which is 3x2. Okay, so that's even inequality. So let's see, this is bounded above by 1/3 of 12 plus 3, which is 1/3 of 15 or 5. Okay, so I'm learning that you can't do better than 5 here. You might guess that I can achieve 5 because of this equality, whereas these were inequalities, but you can't. I'm sort of not yet choosing the best constraints, actually. It actually turns out that the optimum of this problem is actually equal to 4.75, I think. Okay, so I found a pretty good upper bound, but it's still not perfect. So what is this game that we're playing? We're asking how good of an upper bound can we get, where we're looking for an equality of the form d1x1 plus d2x2 is at most h. So that's coming from here, for example. Okay. H was 12, d1 was 4, d2 was 8, right above. What did we need in order to get this bound? We wanted d1 to be at least 2, so that I could get an inequality here. I needed d2 at least 3, so that I could get an inequality here. And what did I want h to be? I wanted h as small as possible. Just to get the best upper bound I could find. So first I found an h of 12, and then 6, and then 5. Questions so far? Okay. I'm just gonna like take this and copy and paste it. So we're trying to maximize this function. And to see what good upper bounds are, we want inequalities of this form, where D1 is at least 2, D2 is at least 3, and H is as small as possible, so we get as good of an upper bound on the optimum as possible. How do we do this? Let's be a little bit more rigorous. To obtain these constraints, we're taking linear combinations of the constraints that were handed to us. So, let's write this out in generality. The most general thing I could do is take y1 copies of this first equation, 4x1 plus 8x2. And I could take y2 copies of the second equation, 2x1 plus x2. And I could take y3 copies of this third equation, and what is this bounded from above by? It's bounded from above by 12y1 plus 3y2 plus 4y3. Now 12's coming from here. And this 3 is coming from here. And this 4 is coming from there. Okay, so this is going to be our H. These are possible H's that we can obtain as upper bounds. This is going to be our D1 x1 plus D2 x2, but I really want to solve for x1 and x2. So I'm going to combine like terms to get x1 and x2. How many x1s do I have? I have 4y1 plus 2y2 plus 3y3. Those are the x1s coming from here and here and here. And how many x2s do I have? I have 8y1 plus y2 plus 2y3 coming from here and here and here. One thing that we need in this game is we need our y's to be non-negative, okay? The y's are telling me how much of each equation do I take. And I need those to be non-negative because if I take a negative of an equation, then the inequality reverses and I'm not getting an upper bound anymore. Okay, so this is important. I need my y's to be non-negative because I want to take an equation, with non-negative coefficient so the inequality sign doesn't switch. If it switches, I no longer can get useful upper bounds. Okay, so remember, we're trying to make H as small as possible with D1, here's D1, at least 2, and D2, here's D2, at least 3. Okay. So we're trying to make this as small as possible, and I have constraints. This is at least 1, and this is at least, sorry. On the left, this D1 is at least 2, and on the right, this D2 is at least 3. So that sounds like an optimization problem. Okay. So to find the best y1, y2, and y3, giving us the best possible upper bound, we solve an optimization problem. I'll call it a dual linear program. Okay, so we're trying to maximize H, which is 12y1 plus 3y2 plus 4y3. So we're trying to minimize H. We want our upper bound to be as small as possible. subject to, and then I have constraints where D1 is at least 2. So 4y1 plus 2y2 plus 3y3 is at least 2. And D2 is at least 3. And I have non-negativity. So it's almost like I pulled a fast one on you, right? I was trying to like find upper bounds on this primal linear program, and I got this dual linear program. It has a lot of the same numbers, right? 2 and 3 appear, 12, 3, and 4 appear. And then this matrix of coefficients has actually been transposed. So, 4, 8, 4, 8, 2, 1, 2, 1, 3, 2, 3, 2. Questions so far? So how well do you do when you bound these linear programs? You actually do as well as possible. You find a bound that is equal to the optimum. So our dual linear program, drawn right here, has an optimum where these are the values of y, and the minimum value, the best upper bound we can find, is equal to 4.75. And then the original linear program, just in terms of x1 and x2, has the same optimum. So it also has optimum value of 4.75. Okay. So linear programs are simple in part because the dual programs receive the same optimum. More generally, in convex programming, there's something called a duality gap. When you take the dual of a more general convex problem, so that the optimization function doesn't have to be a linear function, just a convex function, there's something called a duality gap. These two numbers don't need to be equal, even though one still bounds the other. So in summary, we started with our primal linear program, our original one drawn on the left, and I derived for you where this dual comes from. It comes from finding upper bounds. You want your best upper bound to be as small as possible. That's why we're minimizing these things. And then to obtain an actual upper bound, we need D1 and D2 to be at least 2 and 3, so that we can abound this term by my linear combination of these constraints. So let me show you the notation for taking a dual of this type of problem a little bit more generally. So more generally, the dual of maximize C transpose X subject to AX is at most B and X is at least 0 is to minimize. So these coefficients here are B transpose Y. Subject to, what are my constraints? This matrix here is A transpose. Okay, so let me write down matrix A. Matrix A is 4, 8, 2, 1, 3, 2, coming from these coefficients. And then when I transpose it along the columns, I get 4, 8, 2, 1, 3, 2. So what I have in the dual program is A transpose times the vector Y is at least, this vector is my vector C. And the Y's are non-negative. Okay. So there are two duality theorems that I want to describe, weak duality and strong duality. So the weak duality theorem says if you consider any feasible solution x to the primal linear program and any feasible solution y to the dual linear program, then the optimum of the primal original program is bounded from above by the dual program. That shouldn't be surprising to you. That's how we obtained the dual program in the first place. Remember, we were finding these upper bounds, h. Okay. So if the primal is unbounded, that means in this maximization problem, I can make C transpose Y as large as I want. Okay. So if C transpose Y, if C transpose X gets as large as I want, that means B transpose Y, when I'm trying to minimize in the dual, it can't be anything, right? I can make C transpose X as large as I want. So there's no value for this that I can obtain, B transpose Y when I'm trying to minimize it, right? Because if you said like, hey, I think, I'm trying to make B transpose Y as small as I want, but let's not be greedy. Let's just see if I could get B transpose Y smaller than 1,000,000, right? Well, you can't, because I can make C transpose X 1,000,000,000, and then B transpose Y has to be at least 1,000,000,000. So if the primal is unbounded, then the dual is infeasible. You can't obtain any value for B transpose Y because C transpose X can be as large as you want. Okay, and then reverse, if the dual is unbounded from below. So in the dual, I'm trying to minimize this. So pretend I can make that as small as I want. It could certainly be negative because the coefficients in B could be negative. So pretend I can make this negative 1,000,000,000 or negative 1,000,000,000,000, right? Then that means that the primal is infeasible because I can't even get away with, I can't even find a feasible solution that has a poor value of negative 1,000,000 because I could make the dual problem have a minimum of negative 1,000,000,000. And then, yep, negative 1,000,000 is not even obtainable. The strong duality theorem shows that there's no duality gap in linear programming. So the optimal feasible solution is X to the primal problem, and the optimal feasible solution Y to the dual problem, they satisfy equality. Okay, so the strong duality theorem is saying more than the weak duality theorem. It's a little harder to prove, but both are quite important. We already saw an example of the strong duality theorem up above, where both our primal and our dual had the value 4 3/4. Any questions?
Isn't it the case for convex optimization that the strong duality theorem always holds? Is that right?
My understanding is that convex optimization is where not only is the domain convex, but the optimization function is convex, right? But it could be more general. It could be a convex polynomial or something. Mm-hmm. So my understanding is that there still is a weak duality theorem. So you still have a bound from above by the dual, but the bound is not always achieved with equality. So the weak duality theorem, there's still a version of that, but the strong duality theorem doesn't necessarily hold. And this duality gap is how far apart you are between the solution to the primal and the dual.
Yeah. Then the other question I have is, this is going from the primal to the dual is simply some, geometric transformation. Do you have a good way of visualizing what the dual looks like with respect to, say, if you had your polytope that's just a square, what that's going to look like in the dual?
That's a really good question. I don't, and I should, because I'm a very geometric thinker and not algebraic. So, I mean, algebraically, it looks like we're doing some voodoo magic to go from the primal to the dual, right? It's like we're just doing alphabet soup, and you feel like you have to memorize how C goes here and B goes here and A gets transposed and the max becomes a min. You know, it just feels like made up, right? I mean, we did derive it.
Yeah.
And it's worth thinking through this derivation again, because it's a little mind warping. Great question, Patrick. I'll have to get back on to you on that. Like geometrically, what happens to the feasible region when you take the dual? A couple comments is that, you know, unbounded feasible regions become empty, right? You see that? That's sort of what these are saying. Feasible regions that are unbounded in a certain direction become empty feasible regions.
So it lies in the null space.
Yeah, I mean.
Well, that may be not the right way to say it, but from linear algebra perspective, perhaps, maybe.
Yeah, it's yeah. I mean, I won't try to make anything precise there, but yeah, if the primal polytope goes off to infinity in a direction in which the optimization function can be increased, then the dual problem is infeasible.
Okay.
So maybe I can say one thing about your question, Patrick. This is what determines the primal polytope, right? But the dual polytope depends on more than just that. The dual polytope also depends on C, right? So the dual polytope depends on more than just the information in the primal polytope, because it also depends on C. So, so this might be harder to picture. Yeah. And your first question was about like the strong duality theorem. Does it exist in convex programming? Let me just say that there might be particular convex problems where people have proven that that this equality is achieved. But in general, I don't think it is.
Cool. Thanks.
I mentioned at the beginning of class how I think there's a great qualifying exam question here, and what it is, maybe I want to do so with arbitrary letters C, B, and capital A, but maybe with the particular variables here, I would ask, from this primal program, like step through your logic, which allows you to derive this dual linear program. Okay, so step through your logic that leads to this dual program. I think that's a great sort of qualifying exam level question. I guess I'm signaling a little bit intentionally, but I like it. And how would I do this? I start with this linear program and then sort of explain how we want to take constraints and linear combinations of constraints to get upper bounds. And then here's a general equation for the type of constraint you can get. Here's the upper bound it gives. And then we want to minimize that upper bound. We want our upper bound to be as good as possible, subject to the constraints that for that bound to work, this needs to be at least 2, and this needs to be at least 3. So I think if you can walk through that, you really understand duality of linear programming quite well. And it's worth being able to walk through that, because if you can't walk through that, if you're really just memorizing algebra, then math becomes a little bit less fun. Okay, any last questions? Thanks.